professional student. He just graduated as a master's student from electrical and computing engineering at Purdue, like one of the best departments of Purdue. And Parth worked with me and our collaborator in Zilling University on machine learning, dealing with seismic noise that we see in every day. So Parth.
Let us begin. So, hello everyone, welcome to my talk. It is titled Characterizing Traffic-Induced Seismic Data, Machine Learning versus Domain Experts. So,
Oh, it's still not working again? It just
okay.
worked, yeah.
It's like it sometimes. So, for example, in any urban environment, one event that we see a lot is people driving their cars. And these vehicles generate seismic waves, albeit in very low frequencies. And these waves can be recorded using seismometers. And so we can use seismometers to capture a lot of traffic data. And instead of relying on traditional methods such as cameras to detect vehicles, we can use seismic waves captured by seismometers to count the number of vehicles in any urban environment. And why might this be useful? So first of all is monitoring. So by using cameras, there is a potential for a lot of breach of privacy, where people and their personal details can be leaked, especially in this age of AI, where if your identity gets leaked, it can be replicated all over. And so seismic waves and seismic monitoring gives us a way to perform monitoring in a much more discrete way. So whenever we want to visualize any seismic waveform, and in this case a traffic waveform, we have our time domain data. And looking at the time domain data of a vehicle, we can't really tell what's happening. We can see that there's a lot of high energy along time equal to 4 and 8 seconds, but beyond that, we do not get any additional information. However, urban seismic events have unique signatures in the time frequency methods, especially spectrograms. So if we represent this data in the form of a log-mail spectrogram, we can see that a vehicle event can be very well characterized, as now we are localizing the event not only in time but also in frequency. And here the line in white is essentially the sum of the power spectral density from 40 Hz to about 100 Hz. And here we can see that this sum has a triangular shape, where as the vehicle moves closer and closer to the sensor, the energy goes on increasing in the higher frequencies, and then as the vehicle goes away, the energy dies down, leading to a triangle-shaped waveform. And these features can be very well used to perform many sort of detection techniques, either using statistical methods or using even machine learning. So in yesterday's talk, two of my colleagues, Alejandro as well as Alexa, introduced a way of performing traffic detection using spectrograms. And so in this method, they are calculating two data points. First of all, is the prominence, which is essentially the sum of the past spectral density from 40 to 100 Hz. And if this value exceeds a certain threshold, we say that the value is prominent. And the second value they're calculating is something called as isolation. That's essentially after detecting a peak using prominence, the difference between these two peaks is the isolation. And hence, using these two parameters, they were trying to identify the number of vehicles. However, we can try to detect such events using another technique, that is essentially deep learning. So two of the most common types of networks that are used in deep learning is convolutional networks and recurrent networks. So convolutional recurrent networks rely on patterns and usually in images, where they move a filter across an image, hence essentially performing convolution. Due to this spatial filters, convolutional networks are great at detecting patterns. And in this case, as we are using spectrograms, they can detect patterns across both time as well as frequencies. However, they really lack a notion of memory. So across a particular time series, they cannot really hold a lot of information. This is where recurrent neural networks come in, where in a recurrent neural network, we also have filters, and the filter state at each time index is dependent on the previous filter state, leading to something like this. So as we have a time series as an input and we go from time index, let's say -2 to +2, the filter state at each time index is dependent on the previous filter state, and hence recurrent neural networks incorporate a lot of memory. However, they usually work on time series and are not too great at holding and remembering patterns across time and frequency. And what we want is both pattern recognition and a notion of memory. So essentially, we combine both of these networks to create a new type of network called a convolutional recurrent neural network, or a CRNN. And the structure of a CRNN is quite simple. We essentially stack the CNN and the RNN on top of each other, leading so that the output of our CNN becomes an input to the RNN, and so forth. When we want to perform vehicle detection using deep learning, this is our whole pipeline, where we start with a time domain waveform, we convert it into a spectrogram. This spectrogram then acts as an input to the convolutional network. And in the CNN, we perform pooling, that is essentially downsampling across both the time as well as frequency axis. So hence by performing pooling across frequency at the end of our CNN, our output is essentially a time series, which then becomes the input to the recurrent network, which then tries to fill in the gaps and tries to impart a notion of memory to the outputs of the CNN. And hence at the end of our and at the output of our RNN, what we get is essentially a 2-channel time series. And in this time series, we are trying to detect both the presence of a vehicle, which we call as a vehicle channel, and the absence of all other salient events, which we essentially call is background channel. And essentially, in our case, as we have only 2 channels, ideally both channels are essentially a node of each other. And we also aggregate this output as we take a mean to get another prediction, which essentially informs us whether an event exists or not in a particular time frame. And in this output, essentially we have one value per time bin. And for each time bin of say 0.25 seconds, we have a very high precision, where each value tells us whether an event exists or not for that particular time bin. So essentially, at the end of our output of our RNN, we can get a very precise value, essentially for each time bin of 0.25 seconds. We're able to tell whether an event exists or does not exist. And so, however, we do not directly use the raw results of our network, because we can perform 2 sets of very intelligent post-processing, which are based on our information, or based on our experience in seismic data. So first of all, let's say we have the raw output of our recurrent neural network. This is essentially the probability whether the event exists or not for each particular time in of 0.25 seconds. These outputs are then thresholded with respect to a global threshold. So we convert as a real time series into a binary time series. And we have 2 channels. There is a foreground vehicle channel and a background event channel. However, both of them cannot be true. The existence of a vehicle essentially tells us that nothing can exist in the background. But sometimes, especially at the edges where there is some ambiguity, the network cannot really decide where both exist or not. So in this case, let's say for these 2 time bins, the network predicts that a vehicle exists as well as it does not exist. So in this case, we give priority to the background channel, which is we call informed thresholding. So if for a particular time bin, the network tells us that a vehicle exists as well as does not exist, we essentially give a priority to the background channel and turn off the predictions in the foreground channel. This helps us better localize the event in the temporal domain. And secondly, we know that vehicle events usually last anywhere between 2 and 4 seconds, and this all depends on the speed of the vehicle as well as how far is the vehicle from the sensor. So any events usually shorter than 1 second are results of impulsive noise. For example, over here, we have a positive prediction for just one singular timing of 0.25 seconds, which is most likely is just impulsive noise. So we discard all of these short predictions, essentially turn them off again. And this can again help us to mitigate the total number of false positives. So by performing these 2 rounds of quite intelligent post-processing, we can reduce the total number of false positives as well as better localize events temporally. So the dataset that was used for training this network was a synthetic dataset that had about 200,000 files, which was synthesized using a technique called as block mixing. So why a synthetic dataset? First of all, deep neural networks require a lot of data, usually in the range of hundreds of thousands of samples for effective training. And right now, there does not exist a labeled public dataset that can be used for this. and actually sitting down and manually labeling so many samples is very time consuming and would require a lot of man hours. So synthesizing a data set is a much more effective way. So I would like to give an example of this technique called as block mixing, where we essentially combine a lot of events from many different sources to produce synthetic data. So in order to perform block mixing, this is how we do. So first of all, we take a vehicle event data, and here we can see that we have a triangle shot of spectra, and we trim this data to only contain the salient vehicle event, and we discard the background. Then this data is then filtered as well as windowed. So we filter this data to only contain information above 40 Hz, that is information in high frequency. We also add a window. Then we superimpose this data on top of a file which does not contain any salient event information, only background noise. And so by performing superimposition, here we get a synthetic data where we started with some trimmed event data and some background data to essentially generate synthetic data. And by iterating over a lot of trimmed files as well as some background files, we can generate huge quantities of synthetic data from very small quantities of actual label data. So we were able to generate 200,000 label samples, but only about from 1,500 actual data samples. And in order to perform the evaluation of this network, we used real data files. And so in this case, we had actually 80 data files with 40 files that did not contain any event, which is called background file, and 40 with actual event data. So our actual evaluation data set is much smaller just because performing such labeling is very time consuming. So now I wanted to compare the output results between the neural network as well as using statistical methods, which were developed by domain experts. So on the left, we have a successful prediction using statistical methods. And again, the line in white represents the sum of the path spectral density from 40 to 100 Hz. And the red dot represents the peak and hence a successful detection. And in this case, both methods were able to detect the presence of a vehicle. And here the localization by deep learning is a bit poor, where there is definitely a difference. Both methods definitely agree that a vehicle event exists, but the localization is a bit different. And in the next case, we have a false positive using statistical method, where on the left, if you can see that there is definitely some noise here in the lower frequencies, but this noise is then perceived to be an event using statistical method. However, deep learning tells us that nothing exists. And in this case, we are more likely to favor deep learning results just because this energy is very short occurring. It only lasts for about 1 second. And this is more likely to be impulsive noise rather than actual vehicle event. So as statistical methods rely on amplitude, we are much likely to get false positives due to impulsive events. And here we have an example where we have false positive due to deep learning, and statistical methods are actually better. Where in this case, we have sustained high frequency noise from about time equal to 1 second to about 7 seconds. And as deep learning relies on pattern matching, this pattern is a bit similar to a vehicle event. And so we have a false positive. On the other hand, as we are relying on energy and amplitude for statistical results, here the amplitude of the noise is quite low, and so we do not get false positives. So both methods have their merits and their cons. And finally, there is one huge limitation when it comes to deep learning, that is the limited time resolution of events, where using statistical methods, they were able to detect 2 positive events in this case, as they are quite well resolved in time. However, as you're performing large amounts of downsampling on our actual data, deep learning is not able to differentiate between 2 events. And so instead of detecting 2 vehicles, the network is detecting only 1 singular vehicle event. And finally, both of these networks were tested on long times of real data. So Lee et al. Conducted a study at a location in Singapore, which was beside a 4-lane road, hence predominantly calculating traffic data. And so all of this data was recorded between April and August 2020. So first of all, this graph tells us the total number of vehicle counts starting from about April to August 2020 in this location of Singapore. And all of this data was recorded during COVID. So at the starting few days, we have, that is for about April to June, we have a steady number of vehicles every day. But from Monday to Friday, the total number of vehicles is about constant, and then the number subsequently drops on Saturday and Sunday. And here in this case, both methods agree very well, and the difference between the total number of vehicles is just a margin of error. So we have the first phase of ending lockdowns, after which the total number of vehicles starts increasing. And after the phase 2, where lockdown restrictions were reduced even further, the total of number of vehicles starts increasing. And and using deep learning, we get a very similar result. However, towards the end especially, the total number of vehicles detected has a large delta of about 20%. And this can be due to two results. First of all, the statistical methods might be over detecting a bit due to as more and more people go out, the noise increases, and hence we have more impulsive noise. And secondly, as we have more vehicles, the vehicle events are spaced much more closer together, and hence the neural network is not able to resolve between two events. So even though it might be localizing the events well in time, it's not able to resolve between these two events. And finally, we also have the RD distribution of events at this site, where we can see that initially, the starting days of the lockdown, the total number of vehicles was about constant from about 6 a.m. to about 8 p.m. But as the lockdown restrictions are ending, we get more and more vehicles throughout the day, and we have a lot more vehicles during the peak hours and during rush hour at about 9 a.m. and 6 p.m. And a similar trend is shown using deep learning as well. And especially towards the end, as the lockdown restrictions are ending, we get more and more vehicles towards the night as more people go out. So you have one final slide. So deep learning, so statistical methods essentially are based on the relative power of the event as compared to the noise. On the other hand, deep learning is based on template and pattern matching. Statistical methods are computationally inexpensive, while deep learning is very, very expensive. Statistical methods require less data for parameter tuning, but while deep learning requires hundreds and thousands of training samples. Here, the parameters of the technique might need to be tuned depending on location or time of day, as well as noise characteristics. Such parameter tuning is not required for deep learning, given you have enough training samples. Then statistical methods have relatively worse temporal localization as compared to deep learning, where the localization in time is much better. However, we were able to use deep learning for detecting pedestrians as well, just by adding more training data. However, if you want to detect pedestrians using statistical methods, we definitely need to develop more novel strategies where a lot of more time investment is required. On the other hand, for deep learning, it is very easy to extend. All we need is additional training data. These are a few references of my talk, and thank you.
I'm wondering how you deal with, it's about the background noise versus the noise of the event. What if, for example, there's a really intense rainstorm, and so all the impacts of those rain droplets, the thunder, and so on, would that kind of increase the background noise and then make it more difficult to localize the event?
Yes, that is definitely something that we did see, where whenever we have thunder and rainstorm, how that shows up is we have a lot of impulses, but in higher frequencies, that is especially above 100 Hz. So if you are trying to actually perform vehicle detection, it does not really affect the performance of the network, just because the spectrogram or the signature of rain is so much more different as compared to the signature of a vehicle. So in this case, especially, I can actually go back to one of these slides. Yeah. So over here, if you can see, there is a peak, especially I think this is around 27th of June. So over here, and we get a similar peak over here as well. These were the days where this was a day where there was a lot of thunderstorms, especially in Singapore. So we do get a lot of false alarms, but this is definitely an outlier, but this only happens when there are extreme rain and thunderstorm. So if there is like light rain, it does not really affect the performance of the network.
Why do you need so many training? I mean, it seems to me that, you know, they aren't that different from one another. So why do you need hundreds of thousands of events?
So this all depends on how huge are actually, how complex our network is. So in this case, our network is quite complex because first of all, we have a convolutional network, which by itself has about 6 layers. And after that, we have a recurrent neural network. So in order to have good filter parameters across all of these 8 different layers, we need a lot of training samples. If on the other hand, our network design or network architecture was much more simple, then we would definitely need less training samples. And secondly, what we actually saw over here, so as the days change, so especially here from start of COVID to end of COVID, the actual traffic pattern or the spectrogram of the traffic event changes a lot. Where at the start of COVID, there were less vehicles overall, so the vehicles were much faster as well. So the event was much more localized in time and had much higher energy. But as we had more and more traffic, the event was much more dispersed as the vehicles were slower and they had less overall energy. So the overall pattern of the traffic waveform changes quite a bit. And so when we first trained the network only from data in April, the network performed very well till about mid-June, after which the performance of the network dropped very drastically. So we had to collect additional data samples from each month and then retrain the network to get these results. After which we got much more consistent results.
Maybe we have guests first.
Yeah,
and-
sure.
or-
Of course.
Okay.
Okay.
Yeah.
All right, yeah. Interesting. Neural networks are kind of notorious for being good interpolators, but they can't predict things they haven't been trained with, right? So
True, yeah.
train a lot, seems to be intuitive, but that much, we don't know.
Right.
I was thinking about the following while I was listening. So Alexa's data set might have been dominated by pickup trucks, right? I mean, once in a while, there's an 18-wheeler, we call it in Texas, what is it? Semis here, or tractor trailers, semis. Every once in a while, a light passenger vehicle, probably not many. So you're undersampled with the
Also